Swayam Prabha. Digital India. Educated India.
Hello students, we are discussing the interpretation of thermodynamics with respect to chemical reaction equilibrium, and now we are discussing how to express the Gibbs free energy at a given temperature and pressure in terms of the degree of advancement of a chemical reaction. So we understand that for any composition and temperature and pressure, G is given by a sum of Ni into mu I, where Ni is the number of moles of the ith component, which may be a reactant or a product in the reaction mixture, and mu I is the chemical potential of that ith component at that temperature and pressure that we are talking about. And as Ni is a function of xi, therefore I expect G is also going to be a function of xi. To derive a functional dependence, a functional relationship between G and xi, then what we are going to do is I'm going to rewrite the Gibbs to Hem relation in the following way. Here, what I have done is instead of just mu I have added mu I star, and since I have added mu I star, I will also have to deduct mu I star. So, to maintain this equation, now with this formula, what I am going to do is I understand that what is mu I star. Let me remind you that mu I star at a given temperature and pressure is the chemical potential of the ith component at the temperature, given temperature and pressure, had it been present in the pure phase. And therefore, I can always write down this equation by taking out this portion and this portion separately. So, what would be my resultant expression? Now, I will have G is equal to the part dependent on the chemical potential of the pure species under the given condition of temperature and pressure plus another quantity that I find here that depends on mu I and also depends on mu I star. Now, if I closely look at this term, I understand that this is nothing but G pure, where I have only the pure phases coexisting at a temperature T and P. And what is the next term? Next term is nothing but delta G mixing. That is, if you had the reactants and the products in that composition of the reaction mixture, and if you just mixed them, then what would be the change in Gibbs free energy? That is given by this expression that we have already seen when we talked about mixing of ideal gases. So here is what you are thinking about. You are thinking about the reaction mixture in terms of the fact that I am carrying out a thought experiment where I have one part of the Gibbs free energy being produced by some components present in their pure phases, and these components are having mole numbers exactly equal to what I have for my current reaction mixture. But it is as if they are present but they are not reacting with each other. So this is very close to the ideal gas situation. And therefore I call that this is nothing but the G pure. And I also find that If they are present close with each other, they must be mixing with each other. Therefore, the total Gibbs free energy must be G pure plus delta G mixing. I'm going to take this discussion a little further. I'm going to say that in this case, GTP xi is nothing but G pure TP xi plus delta G mixing TP xi. So where did the dependence on xi come in? That is simply because the NIs that appear in these expressions are dependent on xi. Now going ahead, when I use this particular relationship, I find that I can think of G pure is Ni mu I star. So if I use the definition of Ni and I understand that nu I is negative for all the reactants, therefore if I could have the components of my reaction mixture without mixing for different compositions that correspond to the different extents of reaction, this is how G pure would vary as a function of xi. And if I think of delta G mixing in terms of the composition of the mixture, I know that they depend on the mole fraction of the ith component in the mixture, and the mole fraction xi depends on Ni and Ni depends on xi. And therefore, I know that if I plot delta G mixing, this would give me a relationship, a plot like this. Therefore, as you understand, GTP xi has two contributions at a given value of xi. One is this shown by the blue line, which is uniformly decreasing as we go from the pure reactants to the pure products, having a mixture of reactants and products, having a combination of reactants and products in between for any intermediate composition. And if I now consider the delta G mixing part, I should find that for a given value of the xi, this contribution will be decreasing, and after that the delta G mixing contribution will be increasing. And therefore, if I combine these two terms, I'm going to see how G is for a given chemical mixture is going to change as a function of xi, and that is going to be something like this. So as you see that once again G as a function of xi is going to show a minimum, and it is also going to show a region where xi increases again. And this dependence of G on xi is very, very important in understanding the relevance of the Gibbs reaction energy in predicting the direction of spontaneity and the condition of equilibrium for a given chemical reaction. Now let us try and put all the components of our discussion together. So let me say that we have defined delta Rg, that is the reaction Gibbs energy, as del G del xi Tp, and for a given very simple reaction like A reversible B, I know that this is nothing but mu B minus mu A. Now I understand that the chemical potential is a function of the composition of the reaction mixture. Now with increasing xi, I would understand, therefore, the reaction Gibbs energy would change. And I would also understand that a spontaneous reaction proceeds in the direction of decreasing xi. So now can I use delta Rg to predict the direction of spontaneous reaction instead of having to estimate the chemical potentials? And this is how we do it. We understand that for the reaction A reversible B, G when plotted against xi would look something like this. Now, if I consider this particular point and find out the slope of the curve at that point, what do I have? I have that this is a negative slope. And if the slope which is given by this quantity is negative, what does it mean? It means that mu b minus mu a must be negative. Or in other words, I would say that mu a must be greater than mu b. Therefore, let me reframe the condition of spontaneity for the forward reaction as I understand that this is spontaneous if mu b is greater than mu a. And that happens when the slope is negative. Now, if I think about the other extreme, where in this region the slope is positive. When can the slope be positive? I understand that the slope is positive when mu b is greater than mu a, or in other words, mu a is less than mu b. So, under such condition, do you think that the forward reaction would be spontaneous? Of course not. In that case, the Gibbs free energy would increase as A converts more to B, and therefore I would say that no, the decrease in Gibbs free energy is associated with B being converted to A, and therefore if I look at the reaction at this point, the reverse reaction is spontaneous. Now let us have a look at the reaction equilibrium. At the reaction equilibrium, the Gibbs free energy at a given temperature and pressure for a given composition must be a minimum. So when do I have it? When I identify the minimum point in this curve. At that point, I must be having then del G del xi Tp equal to 0. And this can happen only when mu b is equal to mu a. Therefore, I understand that this is the condition when the chemical reaction will attain an equilibrium. So let me now summarize the picture that we have shown here. We have defined for the simple chemical reaction A reversible B, the reaction Gibbs reaction energy. This is del G del xi Tp, and this is related to mu b minus mu a. Now, instead of having to look at the chemical potentials of every species present in the reaction mixture, I am going to look instead at the sign of reaction Gibbs energy. So, if the reaction Gibbs energy is negative, I understand that the forward reaction is spontaneous, and such reactions are called exergonic or work producing because the system undergoes a decrease in Gibbs energy, Gibbs free energy in this direction, and therefore this amount which is getting decreased can be used to do useful work in the surrounding. Now, if I have a situation where delta Rg is greater than 0, I understand the reverse reaction is going to be spontaneous, and therefore the reaction that I see here under such condition is endargonic or work consuming. Now, if I have the situation where delta Rg is equal to 0, I would have the reaction at equilibrium. And therefore, it is this situation where the system has attained an equilibrium with respect to the composition or the degree of advancement of the reaction. And here it is neither exergonic nor endargonic. So what we have seen here is, by looking at the reaction, Gibbs reaction energy, we can do away with the task of knowing the chemical potential of the system. Rather, we can think about something which is measurable. Now, you can very easily ask this question. I understand that the reaction Gibbs energy is measurable, but how? What I measure in experiments are the compositions, right? If you go to the laboratory and work with a chemical reaction at a given temperature, which is the laboratory temperature, and at a given pressure, which is your laboratory pressure, what is the quantity that you control in the lab? You control the composition of the reactants, which gives you the different compositions of the product. Therefore, to make all these usable, or at least if I want to predict the condition of chemical equilibrium, then I will have to look for the relationship between this delta Rg and the composition of the system. So let us examine the equilibrium condition for this. So for this chemical reaction A reversible B, I understand that delta Rg is equal to mu B minus mu A at equilibrium, and that must be equal to 0. Is that clear? Now, I understand that the values of mu B and mu A depend on the composition of the reaction mixture at equilibrium. For example, let us take this relationship, which is a little more complicated than a simple chemical reaction like this. So I have 1 mole of methane reacting with 2 moles of oxygen, giving rise to carbon dioxide and water vapor, 2 moles of water vapor, and not water vapor, liquid water. So here for this reaction, the reaction Gibbs energy by definition is given as 2 times mu of water liquid plus mu of carbon dioxide gas minus of the contribution coming from the reactants. Therefore, what is going to be the condition of equilibrium? The condition of equilibrium will be so that at equilibrium, measure the composition of the equilibrium mixture. Then for that composition, do you know the chemical potential of water? If you know that, if you know the chemical potential of carbon dioxide, if you know the chemical potential of methane and chemical potential of the oxygen, then you can express the condition of equilibrium for this particular reaction. But as once again, let me highlight that calculation of the mu for an interacting system is not easy. So let us say how we can derive this chemical equilibrium condition in terms of something more useful. So that brings us to the discussion of thermodynamic basis of the law of mass action, where we adopt or we generalize the concepts that we have discussed so far to introduce what is known as an equilibrium constant. And to keep the discussion simple, I will take an ideal gas equilibrium. So let us say that I have this chemical equilibrium A going over to B in the gas phase, and once the system has equilibrated, there is no apparent change in concentration of either A or B. And therefore, I'm going to approximate this chemical reaction mixture as comprised of ideal gases A and B. Obviously, this is an approximation, but I'm going to use it just to make our discussion very simple. Now, for this mixture, can I write down the chemical potential of the ith component, where I can be either A or B? The answer is yes. I know how to write down mu I for either I or B, and that is going to be equal to mu I naught plus RT ln Pi by P naught. Or if I use the standard condition as 1 bar, P naught equal to 1 bar, in that case, what I can do is, I can write down that mu I, the chemical potential of the ith component of this mixture, is mu I naught plus RT ln Pi. And therefore, I can write down delta Rg by replacing mu B and mu A, mu E, B and mu A by this particular relationship. I find that delta Rg now is comprised of two terms. One is mu B naught minus mu A naught, and the other term is RT plus ln Pb by Pa. And this tells me that I can write down delta Rg as delta Rg naught plus RT ln Q. So what is delta Rg naught? It corresponds to this first term. And this is the reaction Gibbs energy under standard state of 1 bar at a given temperature. What is this second term? This second term involves what is known as the reaction quotient. And this reaction quotient is defined as partial pressure of the product divided by the partial pressure of the reactant. Now, as you understand that, therefore, the reaction quotient reflects the value, or it reflects the information regarding the composition of the mixture that has both A and B at equilibrium. And therefore, for any given chemical equilibrium, if I know the composition of the equilibrium mixture, I can find out Q. And then if I know delta Rg naught, I should be able to find out delta Rg. So the question is, it's very easy to find out the chemical reaction mixture composition. So it is possible to evaluate Q. And you must also realize that the standard reaction Gibbs energy can be determined in terms of the standard Gibbs energy of formation, which have been tabulated in the literature for a very long time for a very wide range of chemical species. Therefore, now you see that task has been simplified. You would say that use the standard tables, find out the standard Gibbs energy of formation of your reactant A and product B. Use them to find out the standard reaction Gibbs energy for the given chemical reaction. Once you know this quantity, and once you know the composition of your equilibrium reaction mixture, you can find out delta Rg. And what is the importance of this relationship? I told you already that it is the reaction Gibbs energy, delta Rg, that decides the condition of chemical equilibrium. Therefore, now I am going to show that at equilibrium, I know that delta Rg is equal to 0? And if that is so, I can say that, okay, let K be equal to Pb by Pa, that is a function of the composition of the equilibrium mixture. Then I can very easily say that delta Rg naught is equal to minus Rt ln K. So all I have done is, from this equation, I have written that 0 is equal to delta R G naught plus Rt ln capital Q at equilibrium. Now what is capital Q at equilibrium? That is nothing but Pb by Pa at equilibrium. So this is nothing but Q equilibrium, and therefore what I have is this is what we call an equilibrium constant, and I'm going to replace the Q equilibrium in this expression by capital K. And now I have this very important relationship that delta Rg naught is equal to minus Rt ln K. Now what does it tell us? Now it tells us something which is very, very interesting. We know that when delta Rg naught is greater than 0, by virtue of this relationship, K must be less than 0. Okay, that is because ln K in that case must be positive, must be a quantity that with a negative sign would give me a positive quantity, and therefore K must be less than 1. Now what does it mean? Then at equilibrium, I must be having that if K is less than 1, then Pa must be greater than Pb. Therefore at equilibrium, which component is going to be favored? The component A is going to be favored at equilibrium. Now if I have delta Rg naught less than 0, in that case this would require me to have minus Rt ln K to be less than 0, which would say that my ln K, this must be positive, and that can happen only when K is greater than 0. Therefore, in terms of the partial pressures, I would say that delta Rg naught less than 0 tells me that partial pressure of A must be less than partial pressure of B. This means that the product B will be favored at equilibrium. Therefore, let me summarize what we have learned in this lecture in terms of chemical potential and reaction Gibbs energy. For the chemical equilibrium, which is in general given like this, I know that delta Rg, that is the reaction Gibbs energy, is defined like this. And in general, I'm going to use a form like this, that mu j is given by Rt ln Aj, where Aj is related to the composition of the reaction mixture, irrespective of whether my reaction is taking place in the gas phase, solid phase, or the liquid phase. So Aj contains information regarding the composition of the jth species in the reaction mixture, and I call it the activity of the jth species. Then I can very easily say that the delta Rg is now related to the composition of the reaction mixture by the given reaction, where Q is known as the reaction quotient, and this is related to the activity of each of the components present in the system. And as you see in the definition, the activity of the jth component is raised to the power nu j, where nu j is the component that appears here and it is also appearing here. And this tells us that nu J is going to be a negative quantity when I am talking about a reactant, and it is a positive quantity when I am talking about a product. And using all these relationships, I find that at equilibrium, this delta R G naught is going to be equal to minus RT ln K, where K is the equilibrium value of the reaction quotient. And this tells me that if I know the equilibrium composition, and from there I can find out the activities as a function of the composition, I can find out K, and therefore I can measure what delta R G naught is. If that information is not available with me, I can always use the standard thermodynamics tables to find out the delta R G naught and predict K as a function of that particular composition. So I will end my discussion over here and say that, well, in the next portion, in the practical applications, you can approximate the activities in terms of numerical values of molalities or molar concentration or partial pressures, depending on the kind of chemical reaction that you have. And therefore, if you cannot measure exactly the chemical equilibrium constant, you can always use thermodynamic data to find out the chemical equilibrium constant. Therefore, what we have done here is as follows. Starting from the simple principles of thermodynamics of open systems, we introduced the condition of equilibrium in terms of chemical potential. Then we said chemical potential is not a very useful quantity to predict the direction of spontaneity and equilibrium. So we introduced the quantity called reaction Gibbs energy and derived the condition of spontaneity and equilibrium for a given chemical reaction in terms of delta Rg. And then we said, okay, can I now predict if a given chemical reaction will be spontaneous in a given direction or not? So then we said, yes, if we know the equilibrium constant, and for a given mixture, if I know the reaction quotient, in that case, I can really predict in which direction the reaction would be spontaneous by evaluating delta R G naught and RT ln Q. And we have also seen if there is no way of determining the chemical equilibrium constant, we can take help of the thermodynamic data tables to find it. I will extend this discussion to the predictions of direction of spontaneity of a chemical reaction mixture in my next lecture. Thank you.